This video is over section 9.9, which is representation of functions by power series. This first slide here tells us the definition of, helps lead us really into the definition of power series. Now, the one that we're going to focus our time on are geometric power series, because a lot of different power series can be closely resembled to a geometric series. So I want to remind you that this information here tells us about a geometric series. And remember, the sum of a geometric series is found by using this formula here. Okay, so what we are told is that we're given this function here, and this function closely resembles a geometric series. So if a is 1 and r is x, then this function that we're given can resemble a geometric series, and it's shown right here. So it might be helpful to write this in the following way. So a is 1 and x is r here. So suppose now I have a power series centered at something other than 0. Suppose I have this centered at 1 instead. So this here can be written in the following way. So this resembles what we had, or what we wanted. We wanted this to resemble this, and it did. And what I can do is I can manipulate this algebraically so that I have a series centered at -1, but still just kind of jazz this up a little bit so it still has this look to it. And the thing that we really need to emphasize is that this must be a 1 and this must be a difference. And as long as I have that, then I identify what A and R are, and then I can proceed with the problem. So this here has done so. It shows us our interval of convergence and so on and so forth. So let's take a look at our first example. In our first example, it says find a geometric power series for the function centered at 0. And we're going to do two parts here. Part A, we want to use the technique shown in examples from the text. So you might want to take a look at those two examples before moving on. And then we're also going to solve this using long division. Since it's the same problem, we're just using two different methods to solve, and we are going to end up with the same answer, ideally. Okay, so in part A, when we're solving this part A, we want to end up with A over 1 plus R, because this is the sum of the geometric series. And this is what we want our expression to look like. So we have 1 over 2 plus x. I need to manipulate this so it looks like this. Now, this should be a minus. We want a minus there, okay? So I need to change these two things. Okay, the first thing I'm going to do is try to get 1, and the way I'm going to do that is I'm going to divide everything by 2. So this becomes 1 over 2, 2 over 2 plus x over 2. Again, trying to make this term 1. Now, I also want this to be negative, so I can write this in the following way. I could say minus a negative x over 2, because minus a negative, it gives me that positive. Now this closely resembles A over 1 minus R. Now, the algebra part is going to be the trickiest part for some, okay? So I can conclude that, so where a equals 1/2 and r is negative x over 2. So now we're going to put this into our geometric series. So we can say, so f of x is equal to this geometric series. Now, side note, remember a geometric series is a r to the n. Okay, so our a is 1/2. Our r is negative x over 2 to the power of n. Now, it's sometimes helpful to write out the first several terms of this so we can see what's happening. And when we do that, we get 1/2 plus 1/2 times negative x over 2 to the first, and we're starting with 0, plus 1/2 times negative x over 2 squared, plus 1/2 times negative x over 2 cubed, so on and so forth. And if I simplify this, I get 1/2 minus x over 4 plus x squared over 8 minus x cubed over 16 plus so on and so forth. Okay, now the reason I wrote this out is because this might be helpful for part B. Okay, so now that we have this, we are interested in finding our interval of convergence. Okay, so since we want to find our interval of convergence, we also want r to be less than 1, because we need r to be less than 1, the absolute value of r to be less than 1 in order for our geometric series to converge. So, because converges in a geometric series. Okay, so when I look at this up here, we have already determined that this is r. So I'm going to plug this in here. So negative x divided by 2 must be less than 1. All right, well, since this is an absolute value, the negative can go away. The 2 is positive, so the absolute value can come off of that. So I have the absolute value of x divided by 2 must be less than 1. Multiply both sides by 2. So the absolute value of x needs to be less than 2. Additionally, we want this to be less than, okay, by the definition of by the geometric series test, this has to be less than 1. So we can conclude that our interval of convergence is -2 to 2. So, and they are rounded because of this statement here. Okay, so therefore this series, this series converges on the interval -2 to 2. Okay. All right, so now we go on to part B. In part B, we want to use long division. So what we want to do is we want to see how this goes into this. So setting it up, in case you have forgotten, looks like this. So we want to know what we need to do to 2 to make it a 1. Well, we'll multiply by a half. If we multiply by half, everything gets multiplied by a half. So this gives me 1. This gives me a 1/2 x. Or better yet, let's write this as x over 2, and I'll show you why in a second. Then remember we subtract. That cancels out. So I bring this down, x divided by 2. Do the same thing. What do I do to this to get this? Well, to do that, I need a negative x over 4. So I'll distribute this to everything here. This gives me a negative 2x over 4, which is a negative x over 2. And then this will give me a negative x squared divided by 4. Change the signs. So then I'll have an x squared, sorry, I've run out of room, x squared over 4. You keep going. So this will be a plus x squared divided by 8, so on and so forth. And what you'll notice is that this, what you get, is the exact same thing that we got here when we put several terms into our geometric series. So we're good to go. On to the next problem. Okay, so for this one, we want to find a power series for the function centered at something other than 0 now and determine the interval of convergence. So just like previously, our goal is to make our function or our expression look like this, because this is equal to the geometric series. Oops, this is an n. Okay, so you can refer to the first slide if needed, but we are now going to center this at 2. So we are going to start off with our given expression, and we need to somehow manipulate this so that it resembles this. Okay, and this is where things will get a little tricky algebraically. Now I'm going to manipulate this and write this as the following: 3 over 3 plus 2 times x minus 2. And here's why. This achieves a couple things. First, it gives us our center. Second, if I distribute this 2 here, I get 2x minus 4 plus 3, and that's the same thing as this here. Okay, so this is getting me closer to what I need, but now remember I need this to be a 1, so I'm going to divide everything by a 3 to make that happen. Okay, and when I do that, 3 over 3 on the top gives me 1. This gives me 1 plus 2/3 times x minus 2. Okay, getting closer. Now, the thing we need to be cautious of is this needs to be negative. Okay, so remember a little trick from the previous one. I can write this as minus a negative because that's the same thing as a plus. So I can say that this resembles a geometric series where a is equal to 1 and r is negative 2/3 times the quantity x minus 2. Okay, so let's plug this information in. Okay, so our geometric series is going to resemble the following. We will have sum n equals 0 to infinity of RA is 1. So I don't even really need to put a 1 there. But then all of this is going to be to the power of n, like so. Okay. So now we're just going to clean this up a little bit. And what I'm going to do is I'm going to distribute this power of n to everything. Okay, so that n goes everywhere. And I get this. Negative 2 to the power of n times the quantity x minus 2 to the power of n all over 3 to the power of n. Okay, this here can't be simplified in a very easy way, so this here is going to be my power series centered at c. Okay, so this answers the first part of the question. Now I need to find the interval of convergence. Okay, remember, since I want to find the interval of convergence, I want the absolute value of r to be less than 1 in order for this geometric series to converge. So we know this here is r. I'm just going to plug that in and see what happens. So I have the absolute value of negative 2/3 times x minus 2. This needs to be less than 1. Well, I can take this negative 2/3 out. So I have negative 2/3, I'm sorry, it's a positive 2/3 times the absolute value of x minus 2 is less than 1. I can multiply both sides by the reciprocal of 2/3, so I have the absolute value of x minus 2 is less than 3/2. Okay, well now I can drop the absolute value and sandwich this in between a positive and negative 3/2. And then I can add to everywhere. So I end up with a 1/2 is less than x is less than 7/2. And again, this is non-inclusive, so it's not less than or equal to 1 in order for a geometric series to converge. It's simply less than 1. So I can say that my interval of convergence does not include the endpoints, and it is 1/2 to 7/2. And that concludes this problem. So this next example here is from CalcView. This one, again, our goal is always the same. Our goal is to get our expression to look like this so that it models a geometric series. And this one here is a little more advanced because we need to use partial fractions in order to achieve this. So what I want you to do is I want you to pause my video and go look at CalcView section 9.9 number 15 and then come back here. So hopefully you did in fact watch that video and understand what was happening. I'm going to show you one more type of video that we will see in this section. But before I do, I want to kind of show you some operations with power series. It's really, pretty straightforward, so take a moment and look at this if you'd like. Okay, here is the last example, and it says use this power series here with the absolute value of x less than 1 to find a power series for this function. It's centered at 0 and determine the interval of convergence. Okay, so if I look at the expression we are given, if I look at this here, I can say that this is equal to these two things. Okay, so I've been told that this here is the same thing as this. Okay, not so bad. So really the long division part has been done for us and it gave us this. All right, so comparing this to what we've been told, the only difference really is this 1/2. Okay, and then everything else kind of falls into place. So what I want to do is I want to try to write this as a geometric series. Another thing I need to pay attention to is this minus sign here. So this is the same thing as this. So I'm going to rewrite this as this. The only difference is I need a 1/2 out here. So we get the following. This is equal to the sum from 0 to infinity of -1 to the n. And then I have a 1/2. I suppose I'll put the 1/2 in front here. 1/2. Okay, times all this. Okay, this one here becomes negative, this is n equals 0 to infinity, 1/2 x to the power of n. This is also x to the power of n. Okay. All right, so then we can write this as a single summation. And I can now move that 1/2 out in front since it's common to both of these. And then I will do the following. This becomes -1 to the power of n minus 1 times x to the power of n. Okay, and that's just taking out a GCF. Okay. Now, it's helpful to write several terms here so we can see what's going on. If I were to write several terms of this, I'd have this 1/2 on the outside. And then I would first plug in 0. When I plug in 0 here, I end up with 0. Minus, then if I plug in 1 for any n, I get a minus 2x. So keep going. I plug in 0, 1, 2, 3, 4, anywhere I see an n, and this is what I get. Then I get plus 0x squared minus 2x cubed plus 0x to the 4th minus 2x to the 5th, so on and so forth. Okay, so a couple things stand out to me. One thing is that my constant is always, or my coefficient rather, is always -2. And that occurs on the odd exponents. The even exponents are always 0. Those all cancel out. All the even exponents cancel out. So this can help me summarize what my summation should look like. I still have that 1/2 on the outside. But now I always have a -2 to an odd power. A -2, I'm sorry, times x to an odd power. Remember, an odd power can be represented, or an odd number in general can be represented as 2n plus 1. So this simplifies to this. I can take this constant and move it out here with this one. And when I do that, -2 times 1/2 gives me a -1 times this summation. Of x to the 2n plus 1. This here is my power series centered at 0. But now I need to find the interval of convergence. And just like before, we want r to be less than 1, but our r is x. Okay, so we want x, the absolute value of x, to be less than 1. So that means from -1 to 1. So these are the endpoints we are going to test. Okay, so I'm going to do that over here. Okay, so when I test this, first I'm going to test x equals -1. All right, so I'm going to plug -1 for x right here, and here's what I get. Don't forget the negative on the outside of the summation. So -1 to an odd power. So I can write this as, let's see here. I can write this as the following. So again, be cautious of this negative out here. -1 to an odd power, this will always be an odd number, will give us a -1. So we have a -1 giving me a 1. Okay, so this will result in 1. In this case, 1 is greater than or equal to 1, which is information regarding geometric series. Since this is the case, this tells me that it diverges at x equals -1. Okay, so remember, in a geometric series, we want this to be greater than or equal to 1 in order for the function, or in order for the series to diverge. Okay, doing the same thing now with x equals 1. There's a negative on the outside of this summation. Now we have 1 to an odd power. Well, 1 to any power is 1. This negative on the outside gives us a -1. Now this here, let's see. Again, we want r to be greater than or equal to 1, the absolute value of this. So if I take the absolute value of this, yes, it satisfies this. So we can say that this also diverges. So, therefore, our interval of convergence does not include the endpoints and is -1 to 1. And that wraps up section 9.9.